All right, so first off, happy Veterans Day. Hope you've had a somewhat decent day of relaxing or just getting random stuff done that you don't normally get to do because you're in school. I know that I have definitely hung out with family more, which is nice. My mom came in town with my niece and nephew, and so the cousins all got to play together, and so it was really exciting. But enough of the personal life. Let's jump into this DYU to make sure everyone knows kind of what to look for. Now, you'll notice this is actually my work through this DYU this time around. I changed a good bit up from the last time I gave this one, and so I had to rework it, and this is what I did. I annotated throughout, right? So whenever I see keywords, that tells me a lot. So like number one, I know we're estimating a proportion of cell phone towers, and so what value do I expect to be captured by literally 90% of the intervals? Well, the whole point of a confidence interval, right, is to capture the population proportion. Please note, I know population's good, but it's not a mean because we saw proportion earlier, and it's never about the sample, right? You don't forget a confidence interval, which let me change my screen. There we go. A confidence interval is quite literally the statistic plus or minus the margin of error. And when we get into sample means, it'll be the same thing. And so you always have a sample mean proportion or standard deviation. The goal is to capture the population value, so don't forget that. Okay, number two, I know at least one person I accidentally circled B when I meant to circle A, but just keep in mind the idea of the width of a confidence interval. If I'm doing a 90% confidence interval, that critical value is 1.645. 95% is 1.96. So remember, those are two of the really common ones, so I just know those, but also you can go and look at the table that I showed you with the formula sheet, things like that. So don't forget to take advantage of that. In fact, do I have a formula sheet? Let me pull this down so it's easy to find. And then formula. How could I not? There it is. And formula sheet. I think this formula sheet has all the tables. Let's see. There she blows. All right, so T distribution. So remember, it's this T that you would want. We'll talk more about what T is later, but 90% and 95%. But you can always also calculate that with the calculator. But no matter what, the confidence level will change the width. What I will point out is we use the same sample. So that means when we talk about my standard error, that's still going to be p hat times 1 minus p hat divided by n. That doesn't change. So I know some of us were thinking it was going to be C, and that's not going to be it because we're using the same sample. Right, so don't get distracted by that. This is all about the confidence level and the width associated. So please notice number 3. I think the majority of us were pretty good on this one. Random condition was stated. The 10% condition, it is safe to assume that 40 is less than 10% of all sneakers that they make. So that was satisfied. But the large counts. Now remember, getting back into hypothesis testing, we worry about n times p, but we don't have a p here, so it's n times p hat, which was 2, right? That is not greater than or equal to 10. And so the large counts condition is not satisfied, but A and B were. All right, jumping down to number 4. I know a couple of people really were distracted by this A here. I think most people remember the 1.645, and I just showed you that on the table. But then some of us wanted to pick A here. But you have to remember to write out your formula, because if you do that, you get statistic plus or minus the critical value times your standard error. And so when we look at that, the statistic here is p hat. It's not the count 32, it is the statistic. So please keep that in mind. And when you do it this way, when you write out that formula, notice like I actually wrote it out here. I did it on the test, or when I worked through the DYU, because I do know this formula really well. Been teaching it, for a long time, and I took this class when I was a senior, way back when I was 18, so 16 years ago. So I've seen this for a while. I think it's 16. Yeah, 16 years ago. Okay, so yeah, I've seen this for a while. But if you write it out, it's harder to get distracted. P hat is a sample proportion. So it's 32 out of 50. It's the 0.64. The Z critical is 1.645 for 90% confidence level. And then P hat's 0.64 in the standard error formula. 0.36 is the 1 minus P hat. It's just there. Okay, so please don't get distracted. Use your formula sheet to your advantage. And I didn't bring it up, but literally, if you go to that formula sheet, don't forget you can always go back to confidence level here. That's what we're trying to calculate, or confidence interval, sorry. And so when I jump down and I'm talking about the statistic, I see my P hat, right? I see my standard error. There's my formulas. So yeah, they're there. Take advantage of that formula sheet. Okay. I was a little surprised at a lot of us on missing number 5. It's important to recognize that Sue has a larger sample size. And I think if a lot of us took the time to think about it this way, we know that a larger sample size results in a smaller standard error, right? S sub P hat. Sirius Black, come here. Hey, leave that fence alone. Sorry, my dog is trying to get out of the fence. That's the square root of P hat times 1 minus P hat divided by N. Right, so we're dividing by N. When you divide by 81, it's going to create a smaller standard error. It's going to create a smaller interval width. So that's why the width of Sue's interval will be narrower. If there's anything that I haven't covered with that, please let me know. Notice, I think some of us did pick C because we were thinking about the fact that the confidence level is 90% for both. But the width is really 2 times the margin of error, but the margin of error is the critical value, which they would be the same, times the standard error of P hat, and so Sue's standard error would be smaller. Okay. All right, number 6. I think we actually did really well on this one. You'll notice some of the big ideas that I crossed out in C and D. So one, when we're talking about interpreting the confidence interval, it's the percent confidence that we are capturing the parameter, that the proportion of all resonance, right? I think D is really easy to get distracted by that word sample, but one of the things that I think a lot of us have been picking up on and I need us to hold on to is when you see 2 answers where you're like, these are very, very similar. Yes, dive into those. What's the difference? And the word all versus the sample, right? We have the sample. Do not forget with confidence intervals, you have the sample, you have the statistic. That's not what you're worried about. You're worried about your parameter, the thing you don't know, okay? I don't think anyone got distracted by the probabilities in A and B, so thank you for not getting caught off by that. And then a confidence interval is not telling us what C is. I don't even know what to say else about C. All right, 7. This one got quite a few of us. So I know one student that reached out about number 7 asked, well, does the statistic always have to be in the center? And so don't forget, when we talk about a confidence interval, the way we define a confidence interval is you start with P hat and you add and subtract your margin of error. And so if you think P hat minus margin of error, that's going to be your lower bound. In the dead center of that is P hat where you started. And on the upper bound, you're going to have P hat plus that same margin of error. So yes, your P hat's always got to be in the dead center. That's why we were able to take we started with 0.55 and 0.77, and we divided by 2. We found the middle. And that's that 1.32 divided by 2. So I know that P hat has to be 0.66, which that actually allowed me to eliminate A right away because 0.66 is above the maximum there, 0.68, or 0.66 is above the maximum 0.64. This lower bound of 0.68 is above the p hat, so that's out. D, 0.66 is within that interval, but it's not in the dead center, right? The dead center of this one would be, I think, 0.73. So definitely not the middle. So you're actually left with B and C at that point. And the big thing you need to recognize is, in order to go from 90% confidence to 95% confidence, you got to be wider, right? So a higher confidence level means a higher margin of error, right? You've got to make that interval wider to become more confident. That's why 0.53 to 0.79 is the correct answer. So it had to have the statistic 0.66, but then had to be a hair wider. Okay, number 8 is the one that I have gotten the most questions about. And so I'm going to show it super mathy, but then I'm going to break it down a little bit more straightforward. And so here's what I want you to recognize. What we essentially have is, I don't know what p hat is, but it's actually not going to matter. What I've got is divided by some sample size. And I went from 100 to 900. So what I did is I took that sample size and multiplied it by 9. Now, not everyone's aware of this property, but it's actually very heavily connected to the distributive property with exponents, which, yes, exponents have distributive properties if it's distributed over multiplication division, right? So you can distribute multiplication over addition and subtraction as an aside, right? So I can do 3x plus 6. So I can distribute multiplication over addition and subtraction. And if I had 3/4 to the second, I can do 3 squared divided by 4 squared, right? So I can distribute exponents over multiplication and division. And so for those of y'all that have done rational exponents, you understand that a square root, same thing as just raising it to 1/2. All that to say, I can rewrite this square root as 2 square roots, the square root of 1/9 times the square root of p hat times 1 minus p hat divided by n. So notice I've gotten right back to that original square root, and it's intuitive for me because I've done it for a while, but I'm going to show you the quick way to think about it in a second. But notice if I multiply those 2 square roots, it's 1 times the p hat times 1 minus p hat, exactly what I got, and it's 9 times n. All that to say, the square root of 1 is 1, and the square root of 9 is 3. So my new standard error is 1/3 of what the original was. We talked about this some during the sampling distributions thing. And so remember, we said if we quadruple n, then the new standard error would be 1/2 of what we had previously. And it's because taking the square root of 1/4. If we multiplied n by 16, then it would be 1/4 of previous width, right? I'm just literally taking a square root of that fraction because it's dividing by n. In the same way, if I cut my sample size in 4th, right, then it would actually double the width. So please just remember, if we increase our sample size, it is going to cause a decrease in that sampling distribution, or the variability of that sampling distribution. So it had to have been A or B, but it's going to be, you got to take the square root of it. That's a big thing. So yeah, please let me know if there's more confusion or anything else I need to explain, but I hope that was a good explanation for everybody. You're taking the square root of that 1/9. Be careful again with 9. This is all about it just interpreting. Don't forget it's all about the all. It's all about the parameter. That's where D, I knew that C and D were very similar, but D is all about sample proportions. C is all about all the voters. Now, it is important to notice the reason why I eliminated A and B is we are looking at a true difference in proportions, right? So A and B, and even I think E, don't refer to a difference in proportions. The whole idea is that we are comparing districts C and M, and so we're left with C. Okay. Now, 10 is another one that some of us were pretty solid on, but others struggled at times. And so please remember that a margin of error is simply the critical value times the standard error. That's it. And so my margin of error is that 0.05 that they want us to limit it to. It's a 90% confidence interval, so 1.645, that's the critical value, times the square root of, and they don't give us a p-hat, but remember, if you're going to be as conservative as possible, or if you're just not given a p-hat, remember we talked about how 0.5 will give us the largest sample size, and if we have the largest sample size, then it's guaranteed to be under the margin of error, and we divide it by n. And you solve that equation. Hold on a second, I'm going to pull up my calculator because it is important to... let's see. I'm going to stop sharing. Right, so fun fact, I went to stop the sharing and it stopped my video. So if it seems like there's a weird cut, that's why. If not, don't worry about it. But remember, I've got an equation. So if you go to the calculator and you just go to algebra and numerical solve, you can type in that equation. I think it was 0.05 equals 1.645 for that critical value times the square root of, now go ahead and make that fraction to make it look pretty, nope, not 5, make sure you check yourself, 0.5 times 0.5 divided by n. And so I've got my equation in there, and just remember you have to get outside that square root, you hit a comma, and then you just have to tell the calculator what variable to solve for. I want to solve for n, 270.603, and so n has to be technically greater than or equal to 270.603. And because it has to be greater than, even if it was 270.003, you would still have to round it up to 271 because it can't be less than it. It's got to be greater than or equal to it. So it doesn't matter how small of a decimal. If it's over a number, you got to go up one. But 271 was the only option. All right. Again, please let me know if you have questions. Here, please note, mu and p are parameters. S sub p hat, that is an estimator for sigma sub p hat, so that is a point estimator. I know some of us, I had two, I think, that said, oh, it has to be estimators. Point estimates, point estimators, same thing. Sorry if that was part of the confusion. But yeah, then p hat estimates p and x bar estimates mu. Number 12, some of these I'm moving through quickly because most of us are actually really comfortable with it, just letting you kind of see what United needed to talk about. So large sample confidence interval for estimating population proportion. I know some of us talked about 10% condition, and that was acceptable for partial credit, but this idea of sample size is sufficiently large, n greater than or equal to 30, that really should have made you think about large counts condition, right? The n greater than or equal to 30, remember, that's actually my central limit theorem. Well, really, sufficiently large is central limit theorem. But that's for means, and we're talking about proportions here. So 10% condition is actually for, remember, using your standard error / standard deviation formula if sampling without replacement. Nothing was said about that here, so yes, usually, but that's all only for the sampling without replacement. Large counts is necessary for an approximately normal sampling distribution for p hat. All right. A single interval either captures or doesn't capture. It's a 50-50 shot. That 95% confidence level, remember, is about the long run probability, so you have to interpret it that way, but it captures the parameter 95% of the time in long run. And this is important. I didn't hold anyone on this, but it is a good note if it's unbiased sampling, right? If you have biased data collection, your data is crap. It doesn't matter how good your inference procedures are. All right. I showed my work there for calculating the statistic and margin of error, which essentially I take care of in number 15. And so there you go. I averaged my bounds, found p hat, and then there's a few different ways to find that margin of error, but please notice for the margin of error, all I did was I found the distance from the upper bound to p hat. You could also do p hat to the lower bound, same thing. Most of us, again, were pretty good through here, so that's why I'm moving quickly. But if Farouk increased the confidence level, how would this affect the interval width? The interval would have to get wider to become more confident in capturing P. Please notice that extra detail. Why does it? So, like, one, it has to get wider to become more confident that you're capturing it. But why? Because that Z star increases, right? That critical value increases, so the margin of error increases. So remember, the width is 2 times the margin of error, and the margin of error is your critical value times your standard error. I say it that way just because p hat. Okay. Notice in D, if Farouk increased the sampling size, how would this affect the interval width? Well, I went a little bit deeper. Some of y'all just talked about, hey, if sample size increases, sampling distribution decreases. That's good, but also notice there's a little bit more depth to it of you're dividing by an n, so you're dividing by a larger number, so the margin of error decreases and interval width decreases, so all those details. All right, a lot of us did a phenomenal job here on 16. The big thing I'm going to show is I need you to remember it does not matter what type of inference procedure it is. If you are doing an inference procedure on the AP exam, I don't give a crap what the language says it, unless I show you like the last question here, but it says construct and interpret a 96% confidence interval. You have to use the 4C method for inference. You've got to choose, check, calculate, and conclude. There's no ands, if, buts about it. Do the dang thing. Notice how much space I gave. There's a reason. So what are we doing? We have the president claims that they know at least 1,000 of the 1,800 students, right? To test this claim, the student government advisor randomly selects 100 students and asks the president to identify each by name. So what are we doing? We are doing an interval for the true proportion of students the president can identify by name. Use that language, right? So choose one sample Z interval for a population proportion, or a true proportion, right? Confidence level. If I'm going to claim I'm doing a Z interval, got to say what the confidence level is. Same thing with if I'm going to do a hypothesis test, right? Which is the part of the unit we're in now, then you have to say, so these are my hypotheses, here's my alpha, my significance level, and then always define your parameter. P, in this case, is the true proportion of students the student body president knows. Define your parameter that you're estimating. Then check, same conditions every time, just about. You got to have random sampling for an unbiased system. You got to have an approximately normal sampling distribution. So I've got proportions, so I'm going to use large counts. So you got to pair the idea of large counts with proportions. And then we got to recognize the 10% condition. I made sure it satisfied that 10% condition. And then we got our calculate. You'll notice in my calculate, I didn't do everything that I always recommend. It probably would be a good idea for those who are less comfortable to come to your formula sheet, write that out, right? So statistic plus or minus critical value times standard error, right? So statistic plus or minus critical value times standard error. And then you just pull it from that formula sheet, right? The statistic. So we scroll down. This is again why it's important to identify, hey, it's a one sample Z interval for a population proportion. Statistic is p hat. And then again, if you're looking at these two and you're like, man, they're so similar. Yes, if you have a p, use sigma sub p hat. We don't have a p, so we're using the standard error with that p hat in there. That's a big deal with hypothesis testing, a detail to pay attention to. Okay, so my statistic is p hat. Critical value is a Z star, and there's my standard error formula. And I just filled everything in. Please note, if it was a 96% confidence level, I believe that that's on here. Yep, I was nice. 96% confidence level, 2.054. If you need to, you can also do the 96% confidence level. So the 2% would be in either tail. So you can do probability, distributions, inverse normal, the area of 0.02, right? 96%, 2% in the tails, and same exact value. And if you did the 0.98, I guess it would be, because remember, the TI Inspire only does the area to the left, so I'll show that in a second. It'd be 98%. The other thing that you always have available to you, so I'm going through all the things quickly, is you can open a graphing calculator here, go to functions, nope, there we go, a normal distribution, and what I want is a cumulative probability. So remember, I want to calculate bounds, and let's say, I want the inner to be what, 0.96. There's my 2.054, right? I do recommend zooming into this. Yes, this is the one thing I hate about using the Desmos, is I have to change the scale every time. Negative 0.2 to 0.6. There we go. So, just as a demonstration also for what I was talking about with the TI Inspire, like if I go to the left and I put 0.02 in there, notice that area to the left of 0.02, or the critical value is 2.054 for an area to the left of 0.02. If you put 0.98, that's the positive version, because it would have 2% in the upper tail. Alrighty. But then from there, don't forget, like, I have written this formula out, and I am doing none of that work by hand. I'm pulling up a calculator. So, menu, nope, not 5, because we're in statistics. I've got my option of confidence interval. And again, I know some of us are going to get distracted by this top 4, but we've got proportions, and we got one proportion. So the number of successes was 42 out of 100. Confidence levels, got to change that 96. Nope. 0.96. Always check yourself. And there it is. Lower, upper, margin of error, p hat, and all the fun stuff. But you just pull it in. And so with 95% confidence, this interval captures the true proportion. And notice there's my parameter that I pulled from the beginning. Would this evidence cause you to doubt the president's claim? Remember, that interval of 0.3186 to 0.5213, those are all my plausible values. 0.5 repeating is outside that plausible value, so it's not plausible. I definitely doubt his claim. That's what we would call a statistically significant result when we look at the hypothesis testing later. All right, here, please notice the question is, and so this is the only time. So like if you're at a small piece of a free response question on the AP exam and very little space given, and it tells you assume the conditions are met and just do this thing, and it says focus just on this, that's the only time that you can do skip the choose and the check, okay? But there's my calculations, right? I've defined using my p hat all, p hat seniors, and define that as P1 and P2 to simplify things. I've written out my formula, and then guess what? I didn't do any of that by hand. I just put it onto the calculator, right? Make sure you do 2-prop z-test, or z-interval. And so with 95% confidence, the true difference in proportion of all students the president knows for the entire school versus just the seniors, which really so I actually highlighted in purple. Notice all I did was I took this context. That's the whole thing, the true difference in proportions. That's my context, and I just stole it straight from the problem. Don't make it harder than it has to be. So that true difference is captured by the interval. This definitely provides convincing evidence. The president knows more seniors because a difference of 0 isn't even plausible. Sorry, I'm just rushing, but family and taking care of others is important, and that is me going through the DYU. I will upload this as soon as possible. Again, I hope you have a great day.